Hey everyone, I'm Freddie, and I will be going over this past January contest's gold problem one, find and replace. So in this problem, we are given a string which starts out as only the character A, and we are given a sequence of n operations. Okay, and for each operation, we will be given a character C, okay, and a string S, and we will replace every character, every character C in our current string with the string S. Okay, for example, if our current string is ball and the next operation has C equals L and S equals NA, then ball becomes, these two L's both become NAs. Okay, and so after the operation, our string becomes banana. All right, so that's one operation, and there will be a total of n operations. And Bessie wants to know the string after all n operations. However, since operations, the sum of s across all, the sum of the length of s across all operations is bounded by 2 times 10 to the fifth. This means that there could be an huge, like the ending string could be very huge. So Bessie only wants to know the L through rth character of the final string. Okay, and it's guaranteed that r minus L plus 1 is less than or equal to 2 times 10 to the fifth. Okay, so the string that she wants is not going to be too long. Okay, so how do we approach this problem? First, we'll go over the sample input just so everyone understands what's going on. So the sample input, L is equal to 3, R is equal to 8, and there's 4, so N, which is the number of operations, is 4, okay? And just remember, we start with A, and the first operation turns A into AB, okay? So A becomes AB, since it's 1A, we replace that A with AB. Next operation, A to BC. So we replace all A's with BC. So this A becomes BC. So the entire string looks like this. Then the next one is C becomes DE. So our string becomes B, D, E, B. And the last one replaces every single B with 3 B's. Well, there's 2 B's right now, and they both become 3 more B's. So the final string is BBB, DE, BBB. Okay. And we want to know the third through eighth character. So third character is B, eighth character is the last B. So the answer is B, D, E, B, B, B. Okay. That's a sample input. Obviously, a brute force solution would be to just simulate going through every single operation and substituting as it requests. However, this doesn't work because, as even said in the problem statement, the length of the final string can be very large. For example, you consider, let's say we have one operation. The first operation is we replace A with 100,000 A's. Okay. All right. This is 100,000 A's. Okay. And then the second operation is to replace the same operation, replace A with 100,000 A's. Okay. So after the first operation, our string is just 100,000 A's. But after the second operation, each of those A's becomes 100,000 more A's. So we have actually 10 to the 10 A's, which already is way too big to store or compute or anything, right? In a given time and space bounds. So we must be smarter than this. How do we go about doing this? Well, since we only need the L through rth characters, right? We don't really need to compute most of the string anyway, right? And we can think of this, these type of substitution problems can be thought of as like, like a tree, kind of like a tree, going down a tree. What does that mean? Well, first, I'll start with A, right? And then after the first operation, A substitutes into AB. So A becomes A and B. So like every single character can be like a node in the tree. And every single level will represent like the string after an operation. So after the second operation, A goes to BC, go to B, C, B, right? Because B transitions to B since B is not changing anything, and A transitions to BC because that's what the operation says. Have the third operation, same thing. B goes to B, C goes to D, E, and then this B goes to B. And after the last operation, this B turns into 3 more Bs. This D and E stay the same. The last one is B, B, B. Okay, so this is literally just a tree. And each level, right, all the nodes in the same level just represent the string after that operation. And the last level, all the leaves of the tree, right, represent the final string. All right, so how would this help us? Well, let's say like we just want to compute some continuous subset of leaves, right? We don't want to compute all of the leaves. We want to compute continuous subset. And knowing which subset we need to compute, we can actually remove. We can just not compute some branches of the tree or some subtrees of the tree. So let's say we change this problem. Instead of 384, let's have 684, okay? So L is 6, R is 8, and there's 4 operations still. How does that change things? Well, let's compute this tree again. Okay, so first we have A, right? And after the first operation, we go down A and B, okay? But notice this. Well, what is this? How many leaves does this for the second A have? The second node have? Well, in his subtree, right? If you look down here, his subtree eventually goes to like this, okay? And there's 5 leaves. So A subtree eventually goes down to 5 leaves. But we know that L is 6, right? So that means that all of these leaves are useless. We don't need to compute them at all. So what we can do actually is we can just not compute any of A subtree because we're never going to use that in the answer. So if we knew that A, right, if we knew that this A at the end, he becomes 5 leaves, right? We can just stop computing A there and continue to compute B, right? So knowing how many leaves a certain node subtree becomes at the end can help us to identify which subtrees we don't need to compute. Okay, so now the problem becomes like, given a node in the tree, how do we figure out how many leaves it will eventually, how many leaves its subtree will eventually span out to, right? And this can actually be solved with a DP approach. How so? Well, we can create a DP of every single possible node in the tree. Okay, there should be like a 2D DP. And so the DP will have two arguments. The first argument will be the level, right? Level. This means like this level is 1, this level is 2, 3, 4, and this final level is 5, right at the end. So there's 5 levels. And the second part of DP will be just the letter, right? X. So X is just a letter, A, B, C, D, all the way through Z, right? There's only 26 possible letters. And so the DP, the value of this DP will just be equal to the number of leaves in the node subtree. Okay. So how big is this DP, right? Well, the levels, right? They can be up to 2 times 10 to the 5th possible levels, and there can be only 26 characters, right? So the DP array is around 5 million integers total, or yeah, 5 million integers total, which is obviously within the space bounds. So if we can compute these GP transitions very fast, then we can compute the entire DP table within the time bounds. Okay, so how do we, what does the transition for this look like? Well, first we have to look at the base case, right? This is always when you do. What's the base case? Well, the base case is, right? Let's go back to the example. The base case for the example is the last level, right? Because we know immediately what DP of that last. So DP of 5x, where x is any letter A through Z, right? Regardless of what the letter is, DP of 5x is equal to 1, right? Because the substitute size of any of these last letters is going to be 1. Because there's no more transition out of that, right? It's just the end. It's a leaf in itself. So it only has 1 leaf. Okay, then let's think how about the DPs before it, right? Or how about the levels before it? Well, let's try DP of 4, right? So DP 4, let's say for example, Let's do B, for example, okay? So if we're on the 4th level and we're B, what happens? Well, the B turns into 3 more Bs on the 5th level, okay? So we can actually write this as dp4b or dp5b plus dp5b plus dp5b, right? Because the substitutize of a B at level, a node that has this B at level 4 is equal to the substitutize of level 5 of B 3 times, right? And let's say we want to compute for a different letter, right? Well, any letter that's not B, well, it's very simple, right? So let's do E, for example. dp4E is equal to, well, what happens at the level 4? Well, E doesn't transition to anything. E transitions to itself, right? Over here. E just transitions to itself. So dp4E is literally just dp5E, okay? So these are the two cases. The first case is if the operation at that level is equal to the letter, right? If, like, we can define the operation as, like, an array, so called ops. So ops of level has two variables. We have a .c and a .s, right? C is the character, S is the string that it substitutes with, right? So if when we're computing the dpx, like dp level x for some character x, you have two cases, right? If x is equal to the ops level .c, then we just add, right? We add all of the substituted letters, their DP states, right? So as shown before for the B, right? We added the DP states of the 3 Bs at level 5. But if it's not equal to that, the character, right? If it's any other letter other than that character, then you just increment the level by 1, right? It's dp4, right? And for example, dp4 equals it's dp5e. Okay. So in this, we have written the entire DP. And first, let's write it on pseudocode, and then we can see what the time complexity of computing this DP array is. Okay. So when we're computing DP, so first we set DP n, because n is the number of operations, that's the last level. N, like x equals 1 for each x, right? For every single possible x, right? In A, B, C, all the way to Z, right? But for, let's say we're computing an arbitrary indice of the DP array, so some level and some x. Okay, we have two cases, right? If x is equal to the ops level dot c, right? If the character is equal to the c of that operation, then first you obviously initialize this to 0, and then you sum up all of the substitutions. So for each that's to character next, right? So next to character in operation.s, right? For each character in the string that we substituted, dp of level x, you add that character, okay, for the next level down. Otherwise, so if x is not equal to that level's operation, you just set it to, right? We know it doesn't change. So the substitutize is the same as the if you increase the levels by 1, the same character, right? Sorry, this x. Yeah, and so that's our DP. That's how we compute the DP. So what's type complexity? Well, we know that let's see. For 25 for each level, we have 25. So we have we total for each level 26 different indices, right? So for the 25 other indices, we can be computed all one time, right? All one time, okay? And for the last indice, it is the length of S, right? For that, so length of S. So what is the length of S though? Well, we know that the sum, if we go back to the problem statement, we know that the sum of all S, right, is at most 2 times 10 to the 5th right here. So in this way, we can just say this is just in total, if you sum up of all of the DB states, this equals 2 times 10 to the 5th. Okay. So how many total operations is that? Well, there's 25 times number of levels, which is MO 2 times 10 to the 5th, plus 2 times 10 to the 5th, right? For each transition here. Okay. And this is obviously this is like about, I don't know, 2 million, or no, like maybe 5 million or something. So that's obviously within the space and time bounds. Yeah, so that's just a DP array. Now, how do we use this DP array? Well, this should be pretty obvious, right? For, let's say, if we're computing A, like the same example as before, A goes A, B. So how big is a subtree? Well, this is literally just DP of, right, we're on level 2, and the character is A. So the size of A subtree is just going to be DP2A, okay? So now, how are we going to use this to find the answer to the problem, right? Well, we will do some a recursive, like we will be recursing down this tree, and we want to build a method that recursively goes down the tree and returns the string, the relevant string in the interval L through R, right? So we want some, let's call it like search. So it returns a string, or I can just write this out here. We can do a method. We can make a method string search, right? And well, what will search? What will search has an argument? Well, we know it has the current, right? The current character. Let's call it cur as the argument, as the first argument. The second argument is the level, right? So this marks exactly where we are on the tree, right? So we get character, our current character, and our current level. Okay. So we only want it to return the relevant, right? The relevant string that is but that part of that, the cur level subtree, right? And part of cur subtree that is within L through R. So how are we gonna do that? First, we need to check, right? We need to check if any of cur subtree is even going to be inside the string, right? Because it may be the case, right? It may be the case that we recurse down wrong, right? So let's say we're recursing down, remember the A B thing, right? What if we call the search here, right? And this is like, remember L is 6, R is 8. Well, if we called the search here, then we know DP of 2A is equal to 5. So we know that any of these leaves are not going to be in the final string. So in this case, we can just return. We can just return nothing, right? We can return none, or the empty string. But the thing is, how are we going to know? How do we know when it's out of bounds? Well, we have to keep another variable, and let's call this variable like lower bound, LB, lower bound. All right, this lower bound is just the position we are currently at, right? Because let's say we recursed here, right? So we initially called search on the root, which we obviously would do, right? And then the search recurs down to the children, right? So it determined that this child is not going to be used at all on the string, so it stops recursing there. But for this child, for the B child, right, we need to know, right, he doesn't start at position 0 anymore, right? No, because he has 5 characters that go before him, right? In the final string, right, B, 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 D, E, B, 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 right? Something like this, or something like that, yeah. He knows that these 5 characters before him, so he's actually at position, he starts at position 6. So we can set lower bound is equal to 5 for B, okay? So initially lower bound is going to be 0. And now every time we recurse down, and every time we like skip a computation, we have to make sure to update the lower bound appropriately so that for each recursive call, we know exactly where we are in the final string. Because then we can compute, like, if we are too far, right, if we're before R or before L, or we're after R, okay? So we have a third argument that's called lower bound, LB, okay? So first, before anything, we check if we're in bounds. So when are we in bounds? Or when are we out of bounds? So we're out of bounds in 2 cases. First, we're too far to the left, right? We're less than L. Like the entire subtree, it's less than L in the final string. Or we're greater than R, right? So in these 2 cases, first case, we're less than L. Well, when are we less than L? Well, if lower bound, right, lower bound plus the size of our subtree is less than or equal to L, then we are less than, then we're not within the bounds. So if LB plus DP of what's the size of the subtree, which is DP of level curve, right, is less than or equal to L, or if we're greater, which is just if the lower bound, right, the lower bound is a starting index, is greater than R, right? So this means that we start after the final, right? After the upper bound for the answer. In either of these two cases, we just return nothing, right? Because there are no leaves in our subtree now that are in the final answer. Okay, or you can just return an empty string. Okay. Otherwise, we know that at least some portion of our subtree is needed in the answer. Okay. So what do we do? Well, first we need to check the base case. What is the base case? Well, the base case is what if, right? What's the base case? When we're at the last level, okay? So if level is equal to n, right? Because n is the number of operations. So if level is n, then what do we do? So we know that some portion, so if level is n, first of all, we know that our subtree size is exactly 1, right? Because once we're in the last level, it's just going to be a single letter. And we know that at least part of our subtree is within the bounds, is greater than L and less than R, or greater than equal to L, less than equal to R. But our subtree size is 1. So we know that this character is our subtree, the entire subtree is within the bounds. So we just return the character. So return cur. Okay. Otherwise, if we're not in the last level yet, we have to go down. We have to recurse down, right? We'll go down the tree and recursively call search on all of our children, our node's children. So first, there's going to be two cases, right? One, the case is we are the operation, right? The current operation is going to substitute cur with s, right? So if ops level dot c is equal to cur, right? If the character is cur, that means that our node splits into many children nodes, and then we have to recurse in each of those children nodes. So we do this for I guess for next in ops level dot s, right? So for and next is each character, we're gonna have to recurse down, right? Search lb next, and we increment the level by 1, right? So now we're just recursing on that child, and we have to add this. Well, we have to add the output of that to our current return string, right? So this is define our return string. It's initially nothing, and we add the next whatever the children returned, right? And we do one more thing, right? So just because we recurse on one child, right? Just because we recurse on one child doesn't mean that the lower bound stays the same, right? Because let's say we're A and we recursed on A and B again. If we recurse on this child, we have to update the lower bound because all of these A's child subtree goes before B, right? So we must increment the lower bound. You must increment the lower bound by dp of level plus 1 in A. Okay. So this is what we're gonna do. So LB plus equals dp of level plus 1 next, right? Next is the next thing. And then yeah, keep going, and that's it. And then you can just return ret, right? Return that string. Otherwise, so the second thing is if the operation level dot c is not equal to cur, this means that it stays the same, right? Each letter, that means cur becomes cur at the next level. So we can just recurse. We can just do return. We can just recurse on because there's only going to be one child. LB cur and then level plus 1, right? Because the child doesn't even change. It just right. It's just like if you did A becomes A, right? This is just exactly what this is, right? So there's no operation there. A just becomes A. We're all good. Okay. So this seems like a good solution. However, what is the time complexity of the solution? Well, if you notice, although we are only returning relevant substrings of our the relevant substring of each subtree that we write within the bounds, we still might be checking too many. We still might be simulating too many operations. What does that mean? Well, let's say, for example, our current string was 100,000 A's, okay? 100,000 A's. And L is equal to 0, where L is equal to 1, and R is equal to 100,000, okay? This means every single one of these A's is going to be in our answer. However, what if the next series, what if we have 100,000 operations, okay, that just do this? A goes to A, okay? This it basically just does nothing. So, but each of these, right, in our search thing, each of these ops level.c is equal to cur, right? So each of these operations is going to hit this. So we're gonna have to simulate every single one of these operations. And the final string will be A. It's gonna be the same string, but we're still simulating everything. And this is very unnecessary, but we had to do it because we didn't know, right? We don't know that the string won't be changed. We just know that all these operations are relevant. And so what's the time complexity of this? Well, there's 100,000 operations at each, and there's 100,000 A's, and we have to go through every single one of these A's and every single one of these operations. So we're simulating 10 to the 10. We have 10 to 10 recursive calls in total, which is way too big. Okay. So how are we going to solve this problem? Well, one, we don't really care about operations that substitute a single letter for another single letter, right? So any operation that goes like X turns into Y or something, right? Where these are single letters. So if C is equal to X, S equal to Y. So basically if the length of S is 1, we don't care about this operation because it doesn't change this total substring length, right? We kind of care about it because we need to know what the X turned into, right? But it doesn't change the total length of our subtree, okay? So what if, imagine a world where we only recurse on operations such as like A goes AB, right? Where the size of S is at least 2, okay? So in that world where every single operation, the S is at least 2, well, this means that in every operation, we'll be growing our subtree by 1, okay? And so if we recurse on everything in each of the operations, well, since R minus L is at most 200,000, and at each recursive call, we're growing our subtree size by 1, or we're growing our total leaf size or subtree size, yeah, I guess, by 1. This means that we are going to make at most 200,000 recursive calls, right? Because each recursive call increases the size of what we're working with by 1, at least 1. Okay, so that means we only want to iterate over operations where S is greater than 2. How can we do that? Well, it's actually pretty easy. We only have to edit our DP array one more time. Okay, so we want to store, let's say we can store along with the subtree size, right? We can store a subtree size, but we can also store the next operation such that that node changes into at least 2 nodes. So basically next operation such that S is greater than or equal to 2, and this current node is affected. Okay. So instead of our DP storing only one integer, it's going to store actually multiple integers. So first it will store the let's change this DP. So first it's going to store the size, okay, and it's also going to store we can change it to like a pair. So it's like a C plus. I don't know if people know C++ pairs. Basically, like instead of 1 integer, it's going to be 2 integers. So they have a first and a second. So DP level X is equal to 1, the subtree size, right? Subtree leaf size, I guess. And 2, it's going to be also equal to the next operation that splits the node into at least 2 nodes, okay? And not only that, I guess we also have to know, so it's going to be actually 3 values. We also have to know the next the value of DP level X at that operation, right? Because it might be the case where the letter, like the X turns into like some other letter and turns into some other letter, right? Keeps going. but it's still turning into one letter, so we don't care. But then sometime, like maybe when it's like Z, it turns into like two other letters. We need to know that it at that point it changes into Z. It was Z, and then changes to two other letters, right? Because otherwise, we may have some trouble recovering what the final string is. Okay, so we can do this by yeah. And how is the transition gonna be stored? Well, as you can see, we just have to change a few things. Well, first we need to change like the initial, right? At level n, what is the size? What is the DP array? Well, that's pretty simple, right? It's just going to be equal to, instead of 1, it's going to be equal to 1, and then let's say the second argument doesn't matter because, right, we know that the next operation is supposed to know to do at least 2 nodes. It doesn't exist, right? Because we're at the bottom of the tree, we're at the leaf. So we can set to anything we want. We can just set it to n if we want. And the third one, well, the third argument is going to be the character before splitting, right? The actual character before splitting. Well, I guess for the base case, it doesn't really matter. So it can be, we know that it's going to be x, right? Because it doesn't change. It's not going to split, but it's not going to change either. So our DP becomes 1 and x. Okay. Then the transition is going to look a little different. So we can make DP, or we can make this DP into two things. A pair, we can do like a pair of pairs. Okay. So it's going to be the first in this user is going to be substitutive size, and next will be a pair that just has the next operation, and then the character. Okay, so how we access these values is the first one is going to be DP level x dot first. Second one is DP level x dot second dot first, right? Because it's the pair, and then third one is DP level x dot second dot second. Okay, so these are the 3 values of the DP table. Then the transition. Oh, if let's do the simpler case first. So if x is not equal to ops level dot c, we get this transition is actually still the same, right? Because, well, the subject size is obviously the same, right? The next operation that splits the node into at least 2 nodes, it's going to be the same as if we continue down that path, right? And then the character before splitting is still going to be the same. So this case is unaffected. The case that's affected is this one. If x if x equals the c, the character of that operation at the level, then we first can check 2 things. First, if the s value dot size, right? If the size of s is equal to 1, then we're gonna do things very differently, right? Because if this means that although we're substituting x for a different character, it's still gonna be only 1 character. The string is only length 1. All right. So in this case, we can just actually set the DP value. The DP level x is actually just equal to DP level plus 1 of ops level dot s, right? Because we know that everything follows the same thing because it just changed it to a different character. Okay. Otherwise, so if the length of s is at least 2, that means we know that we split into at least 2 characters. So we can just set DP level x dot second dot first is equal to level, right? Because the next level that we split into at least 2 characters is the current level, and the character that we were when we split is still the same character, right? Because we haven't changed yet. Okay, and this is still the same, and then yeah, so I guess instead of this being just DP level, you just dot first, right? Because we're just only affecting the first value of the DP, right? And then we're done. Cool. So now we have a DP that not only keeps track of the size of the subtree, it also keeps track of when we have splits that we want, right? When we split into these 2 nodes, and when the character that we were when we split into the 2 nodes. Okay. So how do we use this in search? Well, now here is the first thing is still the same, right? If we're adding the out of bounds stuff is still gonna be the same. The stuff expected is gonna be lower than this. So now we're going to be like jumping levels, right? So let's say let's say we had, for example, we had like a node like A, splits into A, into B, and then C, and then finally after C, it goes to D and then E or something, right? Well, we don't care about all of these things, right? We only care about when it splits. We only care about this thing. So we're going to jump from here all the way down to here. And also, if it never splits, then we have to keep track of that as well, okay? So when will it never split? Well, it will never split when the second value, right? Because we know, what is it? We know that for the last level, dp nx is equal to, right, n and then x, right? So we know if dp level x dot second dot first is equal to n, we know that it never splits. Okay, so we have to check. So first, we're going to jump all the levels, and then the return this return value is not going to be if the level is n anymore. It's going to be if dp level cur dot second dot first is equal to n. Right. This means it never splits again, and we don't return cur. We return we return the actual character before splitting, right? Because it may have changed to a bunch of different characters. We know it's gonna be one character at the leaf, but we don't know what character it is. It's just that DP value. That's the character. So DP level, create that second. Okay. So we return that. Otherwise, this means that it indeed. So this case is only if never split. If the subtree never splits into multiple nodes. Okay. Otherwise, this means this case means that it's going to split at some point, and we're going to jump to that point. Okay, so this no longer matters because we know that at that point that it splits, we know that ops level.c is equal to cur, right? Because that by definition is how it splits. So we don't need that. We now we just shift all of this back. For next in ops, it's not the level is different now. It's going to be dp level cur dot second dot first, right? Because that's the new level that we're splitting. So each one you return search this value plus 1. It's the same thing, except we're going to be substituting every level with dp level cur dot second dot first. Okay. Here, yeah, this works as well. Yeah, and here, sorry, this goes at the end. So yeah, exactly, and that's it. That's all we have to do, because we're just going through every single. We're just going everything child of when it splits, because we know there's gonna be at least one child or at least two children, and we add the value that returns, and we increment the lower bound appropriately, and then we return red, and that's it. And what is time complexity is? Again, remember, every single time we recurse, we are splitting, right? We are splitting in the current. We're increasing the subtree size, so we're gonna have at most 200,000 recursions. So the total time complexity is going to be linear for this search algorithm. And what we're going to do in the actual program is, right, we're just going to call search 0, right? Low bound starts at 0, cur starts at A, and level starts at 0. Okay, so this is just going to be the answer. That's the answer to the problem. Search 0 A 0. So I can work. I'm going to now show everyone the actual code that I wrote. So for the problem, here's the code. So in the beginning, we're reading an input, and we have ops array again, right? So ops is going to be stored as a pair. Ops I dot first is going to be C. Okay, ops I dot first C, and then ops I dot second equal to S. Okay, so first is the character, second is the string, it substitutes. Then we create the DP, right? As I said before, we initialize every single ni to be 1 and an I. So I guess this is x in this case. And then we go through and compute a DP array. So we initially start at the n-1th level, and we compute all the way. So we start at the bottom of the tree and go all the way up, right? So for each level, for each I, for each character, right? So in this case, because in C, DP or in C++, arrays, indices. Array indices are always integers. They can't be characters. So I know in the pseudocode, right, we had the DP, the second argument was a character. In this case, I'm just going to map every single character from 0 to 26, okay? So 0 represents A, 1 represents B, 2 represents C, all the way to 25 represents Z, okay? So also I can convert very easily, right? This is a C++ trick. You just add A to I to make the actual letter, right? Because since 0 is A, so if I was 0, I plus A is just A. And since every single character in C++ is represented as an integer, so if you add 1, you get B from A. If you add 2, you get C. If you add 3, you get D. So this is just works like this. So if the character is equal to ops level dot first, so if the character is C, this is exactly what the pseudocode is. Then you first you check, right, if the size of the second is 1. So if S is this length of S is 1, then we're not splitting, right? We don't care about this. So we set this equal to the we set this equal to the next level, the substitution. Otherwise, we set the second, right? DP level I, that second equal to, right? The next time we split is just the current time, so level and then I, and then we go through the for loop of updating the size, right? Otherwise, so if the character, the current subject character is not our current character, then we just set DP level I is the DP level plus 1I, okay? And then we just call search 0, 0, 0. So cur is A, right? But remember A maps to 0, so I just search 0, 0, 0. You look at the search function. So first we check the bounds, right? We have the lower bound, cur, which is our current character, and level, which is the level we're at right now. So again, if we're less than equal to L or greater than R, then we return. Otherwise, right, if the level is N, right, I guess it doesn't really matter. I guess in this case it was a little inefficient. We can combine two of these into one if statement, right? So if DP cur level the first is equal to N, so this can be actually removed without any harm. If DP level cur that second at first is equal to N, then we know that we never split. Okay, this means that we are a node, and by the time it goes all the way down to the leaf, we never split. So instead of returning, so in my search function, because returning strings, because string concatenation can be kind of tedious, instead of returning the string, we have an array of characters, and we just add our current string to that array of characters. Okay. So we just update it's the array of characters with ants, like answer. And so the answer, the count is going to be the current index we're at. And so basically, we're just going to update that index to be the value of the leaf at the end. And then we like increment count and we return. Otherwise, we go through every single, right? When it splits, we go through every single child that it splits into. And we recursively call search on it. And then we update the lower bound. And this one, this last if statement is not very necessary. It's just like for efficiency's sake. So if lower bound ever becomes greater than R, we know that even if we recursed, it's not going to do anything. So we just break anyway, right? Because if we recurse, we immediately just hit this if statement, and this value will be true. So this is just an efficiency thing. It doesn't actually affect the time complexity except for by a constant amount. But yeah, and that's it. So that is the entire problem. It's a pretty interesting problem. It was both a tree type problem and a DP problem combined together. Yeah, and that's just find and replace. Thanks everyone for listening.